Okay, let me do a brief introduction of Ray. I think Ray joined us in 2018, right? So I think the most impressive thing I have is when Ray knocked my door and go to my office and say, okay, she want to join my group. But for the first conversation, honestly, Ray is really super shy girl. I have to ask her, can you repeat what you said again? I asked so many times. So by saying that, I'm really proud of that. Ray grew up from a shy girl to a female material researcher. And Ray have done a lot of things during her PhD study and published papers across different areas, wireless networking, mobile system, and machine learning, even for some COVID paper, right? So the methodology she used also is a lot, like data-driven optimization, differential privacy, also further learning, also some system level implementation. So by today will be Ray's most important day for the defense. But before that, I really want to thank Ray for the contribution to the group. So Ray, I just hand over the stage to you, okay?
Yeah, I think Om is here. Should we take another picture?
Oh, Om is here? Okay, I'm sorry. I cannot include everyone, but yeah, let me do my best, okay?
I can take the picture. As a matter of fact, I can.
Yeah,
okay.
From your
Give
side.
me 1 second. Okay.
Okay.
1, 2, 3, cheese.
No. Can we exit to? Did I do anything wrong? Okay.
No. I already take the picture. Don't worry.
Okay. Please send the picture to me.
Yeah, $5. Okay.
I can invite you for dinner.
Okay.
Okay, Ray, you can start then.
Okay. Thank you for Dr. Pan's introductions. Hello, everyone. Today I'm going to defend my dissertation. The title is Delay and Energy Efficient Further Learning over Heterogeneous Mobile Devices. And nowadays, we are standing in the era of the big data. So recent year has witnessed two cutting-edge technology has transferred the way we live and work. First is the artificial intelligence. The AI actually has become one of the integral part in our life. And with the advanced deep learning technologies, such as the convolutional neural networks, large language models, they have enabled the machine with the intelligence and allows the machine to do faster decision-making and with lower risk. At the same time, we also have a rapid developed wireless technology such as Wi-Fi 5, Wi-Fi 6, and the future 6Gs to provide ultra-high speed for data transmission and support ubiquitous device connectivities. So the combination of these two cutting-edge technology has brought us to a wide adoption of the Internet of Things to ubiquitous connectivity of the smart networks with the mobile devices, and shading the innovation across the field in smart health, the smart agriculture, and smart home and the smart office. Those applications can greatly improve the user experience and makes people's lives easier and more convenient. And at the meantime, thanks to the advanced hardware development, the mobile devices such as mobile phones, the tablet, they are becoming more and more powerful, equipped with mobile GPUs and the 5G chips. So they have the ability to handle the complex tasks for example, the AI intelligent applications. And this is the same devices that interact with us every day and generate a massive amount of personalized data. So it became a trend to push the AI to the edge. For example, we have two snapshots showing that the embedding system actually can do a simple on-device training and inference for image classification tasks. It is good since that the device can collect the data and generate an AI model to improve the user experience. But training solely on the personalized data will lead to an overfitting issue that may degrade the model performance. On the other hand, it's also very risky to directly share the personalized data to other people to do a closed AI training. To overcome this dilemma, a new deep learning technology has been proposed named federated learning. Federated learning recently become a very hot topic for bringing the AI closer to the user and also protect the user privacy. So many of the company has already implemented federated learning into the real world applications, such as multiple healthcare organizations working together to use the federated learning to do CT analysis for COVID-19. And also the Google was the first company to propose the federated learning and applied into the Android keyboard to do next word predictions. And also the CMU is using the federated learning on the agricultural environmental monitoring. In the future, we are expecting to see more applications using federated learning in the field of vehicle signal detections and the VR equipment with robot control. And next, let's see how the federated learning works in terms of model training and protect the user privacy. The federated learning was first proposed by Google, and it's encouraged a large pool of devices to collaboratively train and share the global model. So in a general federated learning system, we have a centralized server that located at the cloud or at the edge of the mobile, at the mobile edge. And also we have a large pool of mobile devices who has their own data sets contain some personal information. And the procedure is as follows. So first, the server will broadcast the model parameter to the clients. And those clients receive the model will perform the local training based on their local data set. After the local training, they will update the model updates to the server for further aggregations. And the step will be repeated until the global model has converged. And during this entire training process, we can see that the data will always keep on the local device, hence the data privacy can be preserved. And meanwhile, the client can learn the knowledge from the other devices using this shared global model. So the model performance and the model generalization can be guaranteed. Despite of all these benefits brought by the federated learnings, it is very challenging, still very challenging to implement the federated learning over a mobile device in practice. Unlike the traditional GPU clusters, the mobile devices are usually resource constrained, so it is very difficult to directly implement the large-scale models into the mobile device due to their memory limitation. And also, the local training and the model updates for multiple iteration can be very time-consuming and power-hungry. So it is also very challenging for the federated learning training on the mobile devices, since they are usually powered by batteries. And also, there are many applications that require real-time feedback, so the training has to consider those delay requirements as well. Last but not the least, the federated learning actually facing a highly heterogeneous environment. Since the devices collected the data by itself, so the data distribution is vary across the devices in terms of the data size, the feature distribution, and the label. Also, the client would have their own preferences to choose the device to perform local training. And since they could located in different areas, so the wireless condition they are facing is also different. And those system and the data heterogeneity will have negative impact on the training process, may slow down the entire training. Hence, it will incur more training time and more energy consumptions. So it is an urge to have a fast and power efficient federated learning design over mobile device to fully unleash the potential of federated learning. And this is the focus of my dissertation. In my dissertation, we are mainly focused on designing the efficient federated learning framework in terms of the energy efficiency and delay efficiency. And in the last summer's proposal, I have proposed two of my works talking about the energy efficient designs. So in the following presentation, I will briefly talk about the idea of one of the two works. And Then I will put more effort on talk about the detail of my work in the delay and efficient federal learning design, including 2 works. First is the service delay minimization for federal learnings. I will talk about how to reduce the service delay from a theoretic analysis. And the second work used to accelerate the federal learning using an overlap scheme design. This work will aim to accelerate the federal learning from both algorithm and the system designs. So next, let's first see the first work, EEFL, a high-speed wireless communications inspired energy-efficient federal learning over mobile devices. In this work, our goal is to reduce the energy consumption of federated training over mobile devices. According to the training process we mentioned before, the system energy consumption of federal learning, including the computing energy for local training for multiple iterations, and the communication energy is for the model updates. And for the computing system energy, we have considered the energy from the GPU, the CPU memory, and the touch screens. And for the communication system energy consumptions, we also consider the energy from the device component like CPU, RF front end, and SoC, as well as the transmission power from the antenna gains. And according to the definition of the system energy, we further find 2 interesting observations in the high-speed network settings. When we consider the advanced wireless technologies, it actually brought us a high data transmission rate, and the high-speed networks actually can significantly save the communication energy, as shown in the following 2 examples. Furthermore, we find that in the high-speed network, it is more often to see that the computing and the communication energy are comparables. So it leads us to think that to minimize the training energies of the federal learnings, we need to trade off the computing and the communication energy. And so we describe our energy efficient problem into 2 questions. First is how to trade off the computing and the communication energy during the training process. And second is how to perform the power efficient on-device trainings. And to answer those 2 questions, we designed 2 corresponding modules, which is the energy-aware adaptive edge policy and the thermal-aware DVFS. For the energy-aware adaptive edge policy, we aim to trade off the computing and the communications. The increasing policy is defined as follows. First, the H0 represent the initial values. The alpha function is the non-negative decreasing function for transmission rate of device I. Delta H is the increment units. And the increasing H policy will adaptively change the increasing speed according to the different wireless conditions to avoid the large communication energies. And here the preliminary result shows that the adaptive edge policy actually has the better trade-off between computing and communication. So they have the smaller energy consumption compared with the fixed edge policies. And then we further design a stopping criteria to avoid unnecessary increasing edge values. Specifically, we design a learning efficient matrix to capture the contribution of increasing edge and also the energy consumption of large edge. And we find out in the later stage, actually, the increasing edge can only bring a small contribution to the model conversion. So when the SE is small, we will stop increasing this value to avoid the large computing overhead. And second, we design a thermal-aware DVFS to perform the efficient on-device training. Specifically, we found out that given the learning task, the energy consumption is jointly determined by the CPU and the GPU frequencies. And for different learning tasks, they actually represent different characteristics. So we introduced 2 learning task specific parameters in our power and delay models. And also to avoid the thermal shorting issues, we propose the following energy minimization optimization problems. And then we use the dynamic programming algorithm to solve this multi-choice snap problem and store the solution in a lookup table. And here is our experiment setup. We consider or build up a in-lab testbed to evaluate the performance of our proposed methods. So the RTX 8000 will serve as the federated aggregators, and we consider two different types of mobile device to do the on-device trainings. Also, we consider a Wi-Fi 5 network settings. And here is the experiment result. We compare with three different baselines. First is the federated average. We consider a fixed edge policy. And LUPA is the state-of-art adaptive edge policy, where we consider a default DVFS scheduling. And we also consider a E adapt edge, which is our proposed method and with the default DVFS scheduling. For different learning tasks, we find out our proposed method can outperform the baselines in terms of the energy reductions. And also the learning specific DVFS in the proposed method is more energy efficient than the default DVFS in the E adapt edge. And next, we further examine the impact on the transmission rate. And we find out that our proposed method actually choose to slowly increase the H value when the transmission rate is very high. And on the other hand, we prefer to quickly increase the H value when the transmission rate is small to avoid large energy consumptions. And next, I will introduce the second work, which is the service delay efficient federated learning over mobile devices. In this work, we are targeted on reducing the training delay of federated learnings over mobile devices. And the service delay actually is determined by the straggler users in the system, where specifically for each round, the computing delay will include the local training for multiple iterations. And the communication delay is for the model updates. And unlike the conventional assumption that assume the communication is the bottleneck, we also find out that in the high-speed networks, the computing and the communication delay are actually comparables in certain scenarios. So we further summarize those conditions for communication-dominated cases. In the communication-dominated cases, we have the condition where we're facing a restricted network speed, which is less than 10 megabytes. And we're using a very powerful devices to do the on-device training. And the model we learn is actually in communication-intensive models. Similarly, we summarize the conditions for computing-dominated cases, where we are having an ultra-high network speed, which is larger than 1 megabyte. And also we use low-end device to perform the on-device training, such as the IoT sensor or smartphones. And also we have the model we training is actually a computing-intensive model. And between those two extreme cases, we actually find many more cases where the computing and the communication are comparables. So under those scenarios, to minimize the service delay, we need to jointly consider the computing and the communication delays. So to minimize the service delay, here we list several factors that can potentially reduce the computing and the communication delay. But since we cannot consider all the factors in one work, in this work, we aim to fundamentally reduce the service delay from algorithm design. So we choose the two different methods. First is to adjust the local update numbers, and also using the quantization scheme in both computing stage and the communication stage. So here, let me briefly introduce the concept of quantizations. The quantization actually is to aim to represent the data in the model weights or in the gradient in a low precisions. So instead of full precision using 32 bits, quantization is actually choosing a much smaller bitwise, such as 8 bits or 16 bits to represent the data. So when you do the local computing, it actually can speed up the computing delay because we are using less bit to do the computations. And the memory space can be also reduced since the low bit wide is stored the data. And also, before we send the model update to the servers, we will first quantize the gradient so we can reduce the data size and corresponding the service delay will be reduced. And next, we will study the impact on both the number of local updates and the quantizations. Here, we first see the impact of the number of local updates. And we see that increasing the age can reduce the communication frequency, but it doesn't always result in the reduction of the service delay. Moreover, we found out there may be existing an optimal value of H to minimize the service delays. And the second one, we further examined the impact on the gradient quantization for model updates. We found out that the gradient quantization level actually have a very important impact on the convergence speed. It is because that if we choose a very small level of quantization, it actually results in a huge information loss for the gradient. Hence, it will require the model to train for extra communication round to recover the model performance. Hence, the small quantization level actually increase the communication rounds and also extend the service delays. And according to this observation, we also find out there existing an optimal value of quantization levels to minimize the service delay. And then we examine the impact on the weight quantizations. Due to the device limitation, we can only use the 16 bits to perform the on-device training on the commercial devices. And we find out that the 16 bits actually can provide the sufficient precision for on-device training, since they require almost the same number of communication rounds as the full precision training, but they can speed up the service delay by 1.6 times faster on the average. And finally, we also examined the impact on the device heterogeneity, and we consider 4 type of devices with different working power and the CPU core. And we find out the structural issue in the system can actually slow down the training for each round. So it is also important to consider the structural issue into the federal learning schemes. And so based on these empirical observations, we proposed a service delay efficient federal learning with weight and gradient quantizations. The key step is shown as follows. The federal learning server will first broadcast the global model to the mobile devices, and the user will first quantize the weight into a smaller size, and then do the on-device training for H iterations. And then the server will compress the model gradient and send the quantized versions to the server for the gradient aggregations. And next, let me first introduce the delay models. In this paper, we consider the computing delay for the GPU devices. Hence, it includes the core computing delay to do the computation, plus the memory access delay to fetch the data and the model weights. And since we're using the weight quantization in the local trainings, so we define the alpha function, and the alpha2 function is a linear function of the weight quantization according to the NVIDIA's documents. And also we consider the communication delay model as follows. The transmission size is related to the model size and the gradient quantization values. And the transmission rate is computing based on the channel capacity with the allocated bandwidth. And for the communication rounds, we are using the upper bound of the convergent analysis to estimate the necessary number of communication rounds for the model convergence. And based on our convergent analysis, we further find out that the weight quantization and the gradient quantization have different impact on the convergence speed. And here, the delta G and the delta W represent the quantization error for gradient quantization and weight quantization, respectively. We found out that weight quantization actually only have the precision, final precision impact on the convergence, while the gradient quantization actually impact the convergence speed, which is consistent with our empirical observations. And then we were using the curve fitting method to estimate the big O notations. And finally, we consider the device heterogeneity. So we allow the user to choose different gradient quantization level based on their conditions. And here we formulate our service delay minimization problem as follows. We first, the objective function is to minimize the service delay over K communication routes. And we consider the model convergence constraint to guarantee the model will converge to a target performance. And here we consider a stochastic quantization schemes, and we characterize the relationship between the quantization level and the quantization errors. To solve this problem, we first find out that to minimize the service delay, the convergence constraint actually is a decreasing function of K. Hence, we can rewrite this constraint into the following equation and replace into the objective functions. And then we will further introduce the auxiliary variables to reformulate the problem as shown in these figures. By further examining this reformulated problem, we actually find that all the inequality constraint is satisfy the polynomial terms. And the equality constraint actually is the nomial terms, and the objective is also the nomial terms as well. So the problem actually satisfies the geometric in the standard form, and then we can equivalently transfer the problem into a log exponential form, which is a convex problem. And then we were using the CVEX solver to iteratively solve the convex problem to derive the feasible solution. And here is our experiment setup. Here we consider two different network settings. For the Wi-Fi 5 networks, we are using the lab testbed to evaluate the performance. And we also consider a 5G networks where we're using the emulator in the Purple Mountain lab. So here we show the experiment results compared with three different baselines. First baseline, we consider assigning the optimal H values, but do not consider any type of quantizations. And the second one, we consider effect PAQ, which they consider the gradient quantization only and assign the same quantization strategies to all the clients. And the last schemes, we will proportionally assign the gradient quantization level based on the allocated bandwidth. And according to the result in the ResNet 20 on the CIFAR 10 datasets, we found out that our proposed method can efficiently reduce the service delay compared with all the baselines. And furthermore, when the transmission rate is high, our scheme tends to select a small value of H to reduce the service delay. And when the transmission rate is very high, our scheme tends to have a large value of H to perform and minimize the service delay. And finally, we find out the service delay for fairy learning is decreases as the transmission rate has increased. And then we will do more experiments on different learning models, and we find out that our proposed method can still efficiently reduce the for the service delay with a very small accuracy drop compared with all the baseline. And here, I would introduce the last work, the walkie-talkie accelerating federated learning by overlapping computing and communication through contrastive regularizations. And in the previous work, we actually consider a conventional synchronized protocols. It is very easy to implement, and we are able to provide a convergence analysis for the synchronized federal average schemes. However, in the highly heterogeneous environments, such protocol is vulnerable to the straggler issues, since all the clients have to wait the new global model to arrive to start the next round trainings. So within the slow device in the system, the other device have to wait and cause a waste of the computing resources. And also the synchronized scheme is very sensitive to the high network latency. So the problem will get severe when the server actually is on the cloud or in the long distance. To address those issues, the existing solution can fall into three options. First, you can do the gradient quantization, as we introduced before, using the compression like sparsification or quantization scheme. We can reduce the model size. However, the compression scheme can only reduce the model size to a certain extent, so it cannot fully address the long network latency issue, and the straggler issue may still exist. So alternatively, we can consider asynchronized protocols. In these protocols, the devices actually can send the model update to the server and get the global model immediately without waiting for the model update from the other devices. However, so they can avoid the straggler issue. However, they do not consider the long network latency, so the training will still very slow when the transmission rate is very small. And the third option is using the overlap implementation. In such implementation, we find out that the server will send the model, and at the same time, they will start the next round training immediately without waiting for the global model or the model update from the other clients. So when the transmission rate is very small, the long network latency actually can bury it into the computing stage. So they have very small training increment the low network speed scenarios. So we see that the conventional interleaving method actually required the new global model to arrive. So they have suffered from the high network latency. However, the overlapping scheme actually is robust to such long network latency and result in a high computing utilization and avoid the straggler issue, since the client will start the local training immediately. So in this work, we are considering using this overlap scheme to accelerate the federated learning. And next, I will introduce how to incorporate the overlap scheme in the federated learning trainings. So since there's no change in the server size, I will just mainly talk about the local training for the federated learning clients. So first, they will do general data samplings and do SJD mini batch SJD updates. And when the time they have to send the models, they will send their fresh model weights or the model gradient to the servers. And when the time the global model has arrived, they have already performed the local training for extra S iterations. So it will cause the inconsistent state for local model and the global models. We defined it as the stillness level and compute in these equations. When the still global information has come, the client will update their local model according to this still information. And the existing work to handle the stillness information using the correction designs For example, like the COCO-D, SJD, they were using a current local gradient, which shown in the blue box, to update the global model and turn into a local model for the next round trainings. And also recently, a state-of-art overlap scheme is named DGA, was using all the global gradients to correct the current local models. In the meantime, they are requiring the user to store the old version of the local gradient as well. So the basic idea of those gradient correction is to leverage the global information in one-step update to correct the local update directions to be closer to the global directions, so that they can bound the model differences between the local model and the global model. However, such differences is related to the stillness level, and we find out that the accuracy actually can drop very quickly when the stillness level is very high and the client has the non-ID data distributions. It indicates that the gradient correction can only bring limited benefits to correcting to bounded the model differences when the data is highly heterogeneous and the stillness in the high stillness scenarios. And also we can see that the state of our DGA do recover some of the accuracy in the high stillness scenarios. However, they require the user to store multiple versions of the local gradient. So they have a demanding memory requirement for the devices, which is not very mobile friendly. And finally, all the gradient correction scheme require the same model architecture for all the clients, since they have to do coordinate-wise the corrections. So it is also an issue for some devices with very limited computing or memory resources. So instead, in this work, we want to introduce a regularization term to always guide the local training with global information to restrict the model differences due to the stillness issues. And the idea is to introduce a contrastive regularization that can automatically enforce the local model to closer to the global model and away from the biased local models, so we can restrict the model differences. And here we shows the result, measure the model similarity using different schemes. We find out that when the stillness level equals to 0, actually two methods, the two overlapping methods actually have a very high model similarity across the local model and the global model G. However, when the stillness level increases, the model similarity in the DGA actually reduced to a relatively small values, while the contrastive regularization can still maintain a high similarity between the local and the global model. And we're hoping this alignment can help to improve and recover the model performance. And next, I will introduce our main design for the local client sites. We consider the network architecture as follows. We have a feature extractor to map the input data into a feature map. And then we'll also connect with the projection head to further map the feature into an embedded space with lower dimensions. And also the feature map will attach to a classification head to do image classification task. And so we will aim to introduce this regularization term in our training objective. Here the lambda represents the hyperparameter, and the contrastive regularization is defined in these equations. The tau here represents the temperature parameters. The aim is the purpose of the contrastive regularization is to minimize the distance between the feature learned by the local model and the feature learned from the global model. And at the same time, we want to maximize the distance between the feature learned by the local model and the feature learned from the model that is in the previous run. So by enforcing these two directions, we're hoping that the model can automatically align with the feature learned by the global models to restrict the model differences. And moreover, we find out that during the training process, since the stillness issues, the reliability of the global model is dynamically changed. Especially in the first few iterations, they have lower accuracy than the accuracy on the local models. And also due to the non-ID dataset, the global model actually have an uneven performance in the first in the first 100 iterations on different classes. So it will incur the unstable federated learning trainings. To avoid such issue, we propose to adaptively reassign the temperature value in the contrastive regularizations. Recall that the temperatures in the contrastive regularization actually is the scaling factor on the similarity between the global model and the local model. Hence, we will design the temperature into a high level if the global model is highly reliable on the class C. At the same time, the client would have very small values or small number of training samples locally. So we will redesign the class-wise regularization terms as follows. So when we have a high temperature for the class C, that means that the similarity on the highly reliable global model will be downscaled, and it will pull the local embedding space closer to the global one. And on the other hand, when the similarity on a unreliable global model will be upscaled, so they will less encourage the embeddings to close to the global model and learn in a more unified way. And here we summarize our the FedCR design in these algorithms. So when the global model has arrived, you can update the local global model as follows. You can use the temperature in ensembling approach to further stabilize the performance of global model. And then you will do the temperature reassigned. And after that, you can start the local trainings to compute the contrastive regularization and do the SJD updates. And then after do the local training, you will send the model to the server. The server will do a weighted aggregations. And here, unlike the gradient correction scheme I introduced before, our proposed method actually can support a subnetwork trainings to accommodate the device with different resources. Specifically, since our contrastive regularization is only performed on the output of the projection head, hence the devices can select different architectures of the feature extractors to fit their device requirement. For example, the low-end device can choose a small number of network partition rates to select a subspace of the network architectures to fit into their memory or computing requirements. So during the training stage, the client can only keep a local subnetwork and further reduce the memory consumptions. And then during the model updates, they only need to send the submodel to the server and also can reduce the communication delays. And finally, the server will receive the global model with the full size to serve into the contrastive regularizations. And here is our experiment setup. We're using the PyTorch to implement our proposed method and other baselines in the simulators. And we consider the image classification task for 3 different data sets. And we also consider a non-ID data distribution in the Reclit distributions. And for the projection head, similar to the previous work, we consider a fixed linear projection to avoid additional computing overhead. So here is our performance evaluations. Recall that since in our scheme, all the clients will receive the same global model at the same time. So our proposed scheme actually falls into the synchronized protocols. And also, so we choose a synchronized protocol to do the peer schemes. And first is the DGA, which is the state-of-art overlap scheme with a gradient corrections. And the LGC is also a synchronized scheme. They consider the structural issue by delaying the slowest device update for only one communication round. And so according to the experiment results in different learning tasks, we actually find out the overlapping scheme can effectively reduce the service delay. Moreover, since our approach can further mitigate the model divergence, and hence we can reduce the number of training rounds and speed up the training time. And here we also examine the overhead for the computation and the memory consumptions. We also compare with different regularization schemes. For example, the overlap prox is introducing a proxy term to do weight alignment instead of using the contrastive regularization. And the overlapping moon actually were using the contrastive regularization, but the projection had include a trainable parameters. And here we can find out using the contrastive regularization, we actually have a better performance than the scheme using the gradient correction or using the weight alignments, especially in the high network latencies. And also compare with the overlap moon, our proposed scheme using the fixed projection had to have less memory usage and the faster training time at the cost of a very small accuracy drop. And here we also evaluate the performance on different data distributions. So for different data heterogeneous levels, our proposed method actually can have a much better speed up and higher accuracies. And also we consider the device heterogeneity. Specifically, we consider 3 types of devices. So according to their capability, they can choose different subnetworks. And since all these other peer schemes cannot support the subnetwork training, we will further compare with another baseline called the HeteroFL, which is also support the subnetwork training, but they only perform on the synchronized conventional way. So we slightly alter them into a overlapping scheme and also compare with the moon, which is with the trainable projectors. And here we further find out, compare with the HeteroFL, our proposed method actually can maintain high testing accuracy, especially on the global models where the P equals to 1. And here we conclude my dissertation. In this dissertation, we observe and study the energy and delay trade-off between the computing and the communications. So we propose 3 different schemes to improve the energy and delay efficiency for federated learning over mobile devices. Specifically, our EFL has developed a transmission-aware adaptive edge policies with temperature-aware DVFS scheduling to improve the energy efficiency of mobile devices. And the second work, the SDE-FL, we develop a joint weight and flexible gradient quantization design to accelerate the federated trainings over heterogeneous mobile devices. And in the last work, we proposed a novel overlap schemes with a contrastive regularization to guide the local training and handle the model stillness, device, and the data heterogeneity in the high network latency scenarios. And last, I will introduce the future work. So in the federated learning, although the server or the other party cannot have the direct access to the raw data, many of the study has found out that the privacy of the training data can still be recovered from the shared model gradient. So here is an example that doing the gradient inversion attack, we actually can recover the basic information of the private data set using a shared gradient. So to prevent the inversion attack, we can consider a differential privacy defense method, which will inject the Gaussian noise into the shared gradient and prevent the reconstructed data to provide any useful information of the sensitive information here. However, when we introduce the differential privacy, we actually have the trade-off among the privacy guarantee, the model accuracy, and the energy consumptions as shown in these concept figures. When we use small DP noise, we actually allow the model to train it in very quick way and have a very high model performance. However, if we want to enforce a strong privacy guarantee, we have to inject a large amount of DP noise. It will cause too much of the noise in the model training and the performance will be downgraded. And we will put more efforts on recovering the performance and leads to a higher training energy cost. So to avoid to have a better trade-off between among these three factors, we can consider a piggyback DP designs. Specifically, we can consider using the gradient compression schemes. It actually prove that the gradient compression, such as quantization and the specification, actually can amplify the DP guarantees, which means that we can use a much smaller amount of injected noise to provide strong DP protections. And that's also the gradient compression can save the communication costs and reduce the energy consumption. And since in the federated learning, the user will use the wireless network to do the model updates. So the white Gaussian noise in the wireless channel can be also served as a free DP sources to further reduce the injected noise and recover the model performance. And this is the future work. And here is the publication of my PhD studies. And that's it. Thank you for your listening. And any question?
Ray, could you check the question from Dr. Han in the chat box first?
Okay.
Dr. Han asked 3 questions, and I think, yeah, the first 2 relate to the quantization work, the second work. The last one is related to, yeah.
Yeah, okay. Let me move to the slide there. So the first question is for quantization, what distribution of the signal to be quantized? So yes, so it is some cases where the weight quantization can exist some non-unified distribution. I think it depends on the learning models. In some learning models, the weight quantization can be it's more like in the Gaussian distribution where most of the values will concentrate in the certain areas, and there are a small amount of value could lead to a long-tailed distribution. So yes, if the distribution is in uniform cases, we can introduce some non-uniform quantization schemes to better represent the data and recover the accuracy there.
I think for your case, the model, the gradient will be the same, right?
Yes.
So there is no such kind of issue. Then, it's not like the input for the gradient quantization will be the same, right? Because the gradient size will be the same, everything will be the same. There is no such kind of issue like Dr. Han mentioned here. But in general, if the input signal they're not uniform, probably some other quantization technique need to be used.
Yes.
Okay,
And
could you step to the second
for
question?
the second question, if the model devices are different, will the different parameter will be used? The parameters, if it's represent to the gradient quantization levels, yes, we
that is
so here we have
if we have device heterogeneity.
Yes, if we have device heterogeneity. So here we consider the assign a different quantization level and the gradient quantization level to fit different devices.
In terms of computing, computing capacity.
Yes, in terms
right?
of computing capacity and communication conditions. Yes.
But I think in the second work, for system level testbed, you only verify 32 to 16, right? So for others, we only do the simulation, right? Other quantization level, we only do the simulation. Okay.
Do simulation, yes.
Yeah.
And for the last question, is there optimally criteria why you combine this in the best way? I'm wondering which part.
I think he want to ask, I'm not sure, I'm guessing. I guess is say for the overlap scheme, is there any kind of optimal solution or optimal upper bound?
Oh, yeah. Ideally, optimal criteria.
So is there any optimal solution to address the stillness issue?
Oh, okay. So I think so far there's still a discussion about how to evaluate the stillness level. So best way is still to check the testing accuracy to see which kind of a scheme has the best testing accuracy to handle the stillness issue. It's still an open question to study the impact on the stillness levels.
So probably I'll change the question in another way. Is there any theoretical work to show some optimal results for the overlapping scheme? Overlapping the communication together with computing in the literature?
Yeah, in the literature, there are works using the gradient correction. They are able to derive the convergence analysis to show that the impact of the stillness to the model convergence. For the feature alignment, I think the theoretic work so far is people are still studying. There's no official theoretic for the feature alignment towards the convergence analysis. Yes. So most of the cases they were most of the work is still do empirical convergence studies to see the impact on the feature alignment.
Could you just clarify, what are you trying to optimize here? So that will also be related to this discussion.
Yeah, so here we, since we want to speed up the federal learning using these overlap schemes, actually it incurs this inconsistent state between the local model and the global model. As you can see, the local model has already S iteration ahead from the global model. So when you include the stillness information, you will incur the out of date information into the model training. So you will cause some unstability in the model trainings. So, and also you can see from this figure, they show that when when you do the overlapping with the inconsistent state, actually the model is gradually deviate from the global directions. So it will cause the model accuracy drop using in the overlapping schemes. So the existing work is trying to use the gradient corrections here to somehow correct the local model directions to be closer to these global directions so that they can hope to recover the model performance there. And yes, so in the existing work, there are theoretic analysis paper to talk about the impact on the gradient correction designs. But in our work, we consider different ways. We want to using the feature alignments to somehow restrict the differences between the global model and the local model. But so far, there's no theoretic analysis to proving the feature alignment convergent analysis here.
So, but sometimes, so are we trying to optimize, the number of these iterations or efficiency or correctness? Because you could probably have a different.
Yes. So we want to.
Is it both or is it one over the other?
I'm sorry. Can you repeat the question?
So when there is divergence, why is it are there instances when even when there is divergence that you don't want to actually make those corrections? Could there be scenarios?
I think or
let me just maybe add one or two phrases there. Could there be scenarios when you don't want to immediately do those corrections, even when there is divergence?
I think in these scenarios, when we consider to train a global model, it is when the goal is to jointly train a global model, I think it's necessary to maintain the local model updates to be closer to these global directions so that they can lead to the global optimal solutions.
Aren't there trade-offs though about how much work you have to do versus how important it is to keep those models, exactly the same as the global optimal?
Yeah. So if the goal is to generate a global model, so we have to consider to restrict the differences between local and the global model. And there is another scenario in the federal learning. It's called the personalized model. So the client will only focus on their local model performance. And in those cases, they will just need to improve the local model accuracies. In those cases, they probably don't care about to converge to a global consensus there. So in those cases, it is not necessary to fix those corrections.
Okay.
Also, if we follow the traditional further learning and training process, right? If you use the communication computing interleaved process, it's kind of similar to this procedure, right? So if you broadcast global model back to all the users, it's like you pull the local training back close to the global model. So all the error correction things and all the regularization things Ray proposed is trying to do the similar thing. We just try to pull the local model training kind of closer to the global optimal. That's the same, right? But I think even for the error correction, they provide some theoretical results is kind of a very loose bound, right?
Yes, the bound of the differences contain the parameter of the stillness level. So when the stillness
the convergence analysis. Oh, okay.
Yes.
Oh, yeah, okay. But that's still very loose. All the convergence analysis bound is very loose, right?
Yeah.
So, yeah, I don't think we have optimal goals for that one, though. I mean, even for the general traditional federal learning training, we interleave the communication computing. It's hard to say there is a optimal results, right? So all the convergence analysis is very loose bound. Yeah. I'm sorry to interrupt. Dr. O, please go ahead for other questions. Yeah.
Yeah, I guess I just have one more question. Thank you for the presentation. I learned a lot from this. What's the biggest unsolved problem in federated learning?
The biggest unsolved?
Yeah.
I
if
think
you had to pick just one problem.
for the biggest unsolved problem, I think this the heterogeneous the heterogeneities in the federated learning is the biggest problems. So the heterogeneity will include the data heterogeneity and the system heterogeneity. So
and
these two.
And why do you believe that?
Yeah, because I think the heterogeneity will significantly impact the model performance, especially for the non-ID data. The federated learning usually have very poor model performance. So there are many works focused on how to improve the testing accuracy, the model performance, and the device heterogeneity, as we mentioned, they can slow down the training process. And also there are devices with different requirements. So the model architecture design is also very difficult. It's very crucial to enable the federated learning on those heterogeneous devices. So I think heterogeneity here is very biggest issue in the federated learning.
And is it also your belief that the devices that would participate in federated learning systems will continue to be more and more heterogeneous moving forward?
Yes, for the scenario, especially you using mobile devices to do the on-device training, the people can use different type of device to participate in the federated learning. So you can use mobile device or using your computers. So the device capability can be various because we have so many different computing devices on the market.
Thank you.
So I think federated learning is if we try to say compare that from networking guy point of view, it's very similar to ad hoc network. There are just so many questions there. I think Ray answered in a very general way. I mean, the heterogeneity includes many things like computing heterogeneity and data heterogeneity, ID, non-ID, also includes, if we talk about wireless communication, the wireless communication capability, heterogeneity as well, because different people have different like to put it a simple way, have different transmission rate, right? So we use Wi-Fi 5, Wi-Fi 6, 5G, 6G, or even LTE, we have different transmission rate. So there are a lot of heterogeneity issue. I think in her PhD study, I mean, for the computing heterogeneity, probably mostly computer architecture guy, hardware guys trying to solve that. And the data heterogeneity, general machine learning algorithm guy, they're trying to solve that. I think for Ray's work, most of them, they try to connect the wireless things with flat learning, try to solve some key issues incurred correspondingly. For example, like communication efficiency, the trade-off between communication and computing, and stuff like that in the flat learning. I think he still try to connect the wireless with flat learning, try to answer the question from our background, something like that. Yeah. Okay. Yeah, you need to answer the question, right? So I can only do that.
Yeah.
So any other question from the committee member?
Yeah, so great presentation. So I only have two quick questions. So the first question is, in one of your work you mentioned the energy efficiency, and I see like that you have some like the total energy consumption, and is that an estimated total energy consumption, or did you actually measure it?
Yes, for the energy consumption, we measure the computing energy consumption from the development kit. And for the communication part, we for this experiment, we use the theoretic analysis for the theoretic network speed to compute the energy consumption here. But in our test bed, yeah, we are able to collect all those energy consumptions from
are you using some hardware to measure the energy, or you are using some software to monitor like within the computer?
Yeah, so for this experiment, we are actually using the hardware measurements.
Okay,
so they are able to provide the CPU, the memories, energy consumptions.
I see.
From those devices.
Thank you. So my second question,
sorry, I mean, I think this is a little bit older version of your taskbar, right? So yeah, our new version taskbar, we also measure the energy consumption of the smartphone, right? You didn't update.
Yes. Yeah.
Yeah, for this development kit, we can use some library, and with they have the inherent library, we can pull out the energy profile. So as you say over there on the computer, we can see that. I think for smartphone, we need external, external devices to measure the energy consumption.
Where it's like the more end-to-end.
Yeah. What's the device name? Is Monsoon?
Monsoon.
Yeah.
Yeah, Monsoon meter.
Yeah, meter. Our monitor. Yeah, something like that.
Yeah. So my second question is more like the a high level one, which is like I saw you use quantization to minimize the total delay, right? So what is your like the decision factor that you decide to use quantization? Because there are a lot of different ways to save the energy. There are quantization, specification, or pruning, right? Is there some specific reason that you choose this one?
Yes, for the quantization, I think we choose this one is it is the most mature application can be applied in the commercial devices right now. So we are able to see the speed up or the improvement on the commercial device other than the quantization or the pruning. Most of them require additional hardware designs to achieve the real trade-off in the devices. So the quantization actually is the easiest way to directly implement on the current commercial device. So this is why we choose this.
Do you mean like there are like the existing package of software that could allow you to implement?
Yes. Yes. Right now the NVIDIA is proposing 16 bits quantization for on-device training. But for specification and pruning, since they have to skip some of the neuron computation, so they require additional hardware designs. So you need specific hardware to realize that.
Yeah, in other words, I think for the TX2 and Xavier, we cannot show the advantage of pruning and weight specification. Because although you prune that to 0, but when they do the calculation, they still, from hardware point of view, still calculate those. So the energy consumption will be the same, unless we need to verify that on FPGA or Xilinx. What's the device called? The Zinc or something?
Yeah, the Xilinx.
Xilinx Zinc. So we don't have those devices in hand. Also, it's need a lot of power knowledge to do that. So
okay, I see.
Not our focus. So yeah.
It's just like in theory they may all work, but in practice it's hard.
Yeah. In commercial devices, only the 16 bits weight quantization is going to work. A gradient quantization works for all the devices, but weight quantization only work for for the
several devices.
Yeah. I see. Yeah, that's all my questions. Thank you.
Thank you.
I also have a couple of questions. Thank you, Rui, for the presentation. So on slide 14, can you say how do you tested the accuracy?
How to test the accuracy?
Yes, on the third figure that you have there. So how do you measure the accuracy?
So the accuracy we're using the Cypher 10 or the Cypher 10 the tested dataset on the server side to do the evaluations. So the testing accuracy, the testing accuracy here is to show the accuracy of the global models using a test dataset. So yes, it's untrained for the client.
With the test beds. All right. And on slide 27, you have there on 27 in the first constraint. The first constraint you have the less or equal epsilon, right? Depending on the desired performance. So how have you chosen epsilon?
Yes, the epsilon here they were chosen according to different learning tasks. Usually it's a very small numbers. It's basically according to the model performance. We're choosing a very small numbers for the Cypher 10, for example, 0.08 for as the target training loss. Yes.
I see. So was it based on the application?
Yeah, based on the application, different tasks we were choosing different epsilon.
Okay, thank you. And a general question. So what was the most challenging problem that you solved during your PhD?
Most challenging problem?
Yes, that you encounter.
I think for most challenging problem is when I transfer from theoretic to doing the system implementation. There are many practical tips or the tricks you need to learn and practice on the testbed results for iterative testing on the testbed to evaluate the performance. So I think the most challenging part is to put your theories into the practice to do the real world experiments. Yes,
that's great that you have such a strong theoretical background, and at the same time that you can also do the test beds. That's great.
Yeah, thank you.
Okay, thank you.
I think the most challenging problem is to find a job, right? So that's the most challenging problem in today's market.
That is second challenging problem.
That's very challenging.
But she has an impressive list of publications.
Yeah. She's a hardworking student, right? Do very well in different areas, theoretical study, also system level. I'm shocked actually. The transfer period for her is very short, from theoretical study to system level implementation, system level kind of research. So I'm impressed, and also I'm surprised. Wonderful work.
Thank you, Dr.